Welcome to challenge question day 2. This one is more challenging than the first one. It also involves a lot of substitutions, applying standard integral formulas when you can recognize it, and applying partial fraction decomposition to help you solve. This one looks simple, however, it is actually pretty tricky. So why not let's see how to solve it. The reason why this question is hard is that we have square root and we have a trigonometry inside. So there are no intuitive solutions to that, and we cannot just use a formula from the formula booklet to solve it. So what we want to do is that we want to try to remove this annoying square root, and we want to get rid of the trig, because trig is always hard if it's not direct, right? So if we can convert the trig to some kind of polynomial or some kind of like rational expression, and then, or if that's still complicated, we can break that into like two separate integrals of something, and that's just pure algebra, and we integrate each part separately. That will just be easier than what we have here. So what we're trying to do in this full video is we are trying to make that thing simpler to integrate, break them apart, make them smaller, make them simpler to integrate. So firstly, we should try to remove the square root and substitute this square root of 10x, right? So let t equals to the square root of 10x. So since we want to get rid of the square root, we should square both sides. And now x is a function of t, so if we want to replace dx, we should take derivative, right? So 2t equals to secant squared x times dx or dt, because it's implicit differentiation. Now, since we want to isolate dx ultimately, right? So let's move dt to the other side. Now we have secant squared x times dx. Well, remember that from trigonometry, we have secant squared x equals to tan squared x plus 1, right? Times dx. So why am I doing this? That's because if we isolate dx right now, we have this thing as the denominator on the other side, right? But like that's still trig, and we don't want trig anymore in our integral. So we are trying to replace that with some kind of variable. So tan squared x equals to this thing squared, right? So that means t to the 4 equals to tan squared x. Now we just use t to the 4 to replace tan squared x. So now we don't have trig anymore, and we don't have square root anymore. So to isolate dx, we have 2t dt over t to the 4 plus 1. And so let's rewrite the original integral. Square root of 10x dx equals to, so that is just, well, square root of t squared, and then times dx, which is 2t, then t to the 4 plus 1 dt right here. So we can simplify that a little. So this thing just equals to t itself, right? The power and the square root reverses the entire thing. So we have 2t squared over t to the 4 plus 1, that thing over dt. So now we have like a rational expression, right? Like a polynomial over a polynomial. But like the power is really high right now. Remember in the last video, like even this thing took quite long to solve. So we don't want to have the power of 4 in the denominator. It will be too complicated. So what we can do is that we can divide the numerator and the denominator by t squared. We end up with 2 over t squared plus 1 over t squared. No, sorry. 2 over t squared plus 1 over t squared dt. That's our first step of removing the undesirable stuff, and there are more substitutions we will involve. So up to this step, the power has been, like, the degrees has been lowered a little bit, but like you still cannot directly integrate that. And a better way is to try to split this into separate smaller integrals, but we need to like write 2 as something else. If 2 is like the sum of 2 polynomials, then we can split this into 2 integrals, right? So a good way is to observe what this can bring us, like the denominator. The denominator t squared plus 1 over t squared. It's kind of like a squared plus b squared, right? Because both of them are something of t squared, right? So if we let t squared equals to a squared and 1 over t squared equals to b squared, we'll set that first. What are the things we can remember from a squared plus b squared? Well, if we have a plus b to the power of 2 minus 2ab, that just gives us a squared plus b squared, right? Because we got rid of the 2ab inside. So if we substitute something of t into this equation, a is just t, then b is just 1 over t. So t plus 1 over t squared minus 2 times t times 1 over t. That thing equals to t squared plus 1 over t squared. You might not understand why I'm doing this substitution and random algebraic manipulations, but you will see later. Because after all of the things I'll be doing, it will suddenly make sense in the end. It's just a very long and not straightforward method of trying to break that rational expression into 2 integrals. So now we have just 2 here. If we simplify it, that just equals to t squared plus 1 over t squared. That's really important. So what else equals to a squared plus b squared? If we have a minus b to the power of 2, well, since there's a minus 2ab here, so let's add 2ab, and then we will get a squared plus b squared in the end, right? So if we substitute t and 1 over t, we'll get something similar as before. So that simplifies into t minus 1 over t squared plus 2 and t squared plus 1 over t squared. So this and this are equal. That means this and this, they're equal. So we have t plus 1 over t right here. So if we let u equals to t plus 1 over t, then if you take the derivative, because we just did something similar to u substitution, we just now have 1 minus 1 over t squared. You will see why I'm doing this later. Let v equals to t minus 1 over t. Oh, that's a little messy. So dv over dt equals to 1 plus 1 over t squared. So if you add du over dt and dv over dt, add them together, you will end up with this and this. You will just end up with 2, right? Because 1 over t squared is just cancelled out. So you have 2. Did you notice that we just managed to convert 2 into 2 polynomials? So, that's because, to write it out and make it clear for you, we managed to split the 2 into 2 polynomials, and they look kind of similar to this denominator we have here, and that will help us to split that into some kind of like 2 integrals later. So if we rewrite this, we will have a big numerator on top. I'll go with 1 minus t squared first, plus 1 over t squared, t squared plus 1 over t squared as the numerator dt, right? So that could be split into another one. If you're still confused about how this whole algebraic process happens, it's just that our main goal is to try to break this into 2 integrals. However, 2 is blocking our way because if we have a number up top, we can't really break it into something easier to help us solve. Well, at most, we can break it into something like, like another number on top, right? And something else, like plus something else similar. But that won't make this integral anything easier. So if we can find an algebraic expression of t to represent 2, like 2 equals something something t plus something something t, maybe something like that, and then we can decompose this into 2 different fraction as in the integrals, then it will be easier to solve. And by looking at this, it reminds us of a squared plus b squared, right? And a squared plus b squared is related to a plus b squared and a minus b squared by plus or minus 2ab, right? As I've talked about before. And if you observe a little more, you'll find that if t is a and 1 over t is b, then plus or minus 2ab will just be plus or minus 2. And if we take the derivative of a plus b or a minus b, which is du over dt or dv over dt, we manage to have t in only one of these terms, and we have another substitution. So that means not only if we add up these two, we can get cancel these two out, then we will have 2. So we have some kind of algebraic expression of t to represent 2 here. We also have this new substitution that later we can take advantage of. And after we break this apart into separate integrals, we can use these substitutions like du and dv to help us have simpler integrals. Like we can replace this with du over dt. We can replace this with, well, that is just u squared minus 2, right? So we replace this with something like u squared minus 2, then we can make this integral a lot simpler. And then by making it so simple and separated, then perhaps we can apply the standard integral formulas or apply something like partial fraction decomposition to solve what's remaining. So the entire process is just to make this thing more solvable by either substituting it with some kind of new integral or breaking it apart into simpler parts. So that's the whole idea. So now let's rewrite this into 2 separate integrals. The first part is 1 minus 1 over t squared over t squared plus 1 over t squared dt plus, why is this so messy, plus 1 plus 1 over t squared over t squared plus 1 over t squared dt. Right, so they only differ by this positive and negative sign in the numerator. So we remember that this thing is du over dt, right? And times dt, so we can have du and dv in here and there substituted to make this thing look simpler, right? So let's try to, so this kind of looks like messy right now. So we should try to introduce u and v inside to make this look simpler, into like a simpler sum of the 2 integrals, and we can try to solve them. So notice that this part equals to du, because this one is du over dt, that's dt, so we have du left. And here, the denominator can be replaced because the denominator equals to this thing, which is equals to, so if we substitute u in there, it equals to u squared minus 2. And we can substitute the same thing with dv and v for this integral. So just by substituting what you have above, you will end up having, that's 1 over u squared minus 2 du plus v squared plus 2 dv. Just make sure you copy them correctly and substituting them correctly, and you'll end up with this. So now we're heading toward something interesting. So here we could later apply partial fraction decomposition. Here we could apply one of the standard integral formulas. If you kind of forgot partial fraction decomposition, you should visit the first challenge question video where I solved this integral, like this one. So yeah, I won't be reintroducing it today. I will just be heading directly in partial fraction decomposition soon. So now we should pull out 1 over 2 from both of these integrals so that the later calculations will be a bit more convenient. So this becomes, let's write it as like something to the power of 2. So now we have this. And so since we pull out 1 over 2, we just have minus 1 to the power of 2. I write this just for clarity. du plus the other one follows the same pattern. So yeah, v over square root of 2 to the power of 2 plus 1 to the power of 2 dv and parentheses. Right, so now we can apply the standard integral formula and we can substitute something for v later. So that's standard, I'll just write the abbreviation maybe, standard integral formula. I'll show you which one. And for this one, I'll be using partial fraction decomposition to solve. But however, if you know hyperbolic tangent, then you can use that to solve too. However, IB doesn't require hyperbolic tangent like this. It's called tanh. We don't require that in IB, so you don't really have to use it. If you set tanh theta to u over square root of 2, you can solve it by yourself if you want, but I won't be using this method here. So yeah, let's do what we do next and just continue. I will be starting with this one because it's simpler. So yeah. The standard integral formula I'm talking about for this is something we also saw in the last video. It's just the integral of a squared plus x squared dx equals to 1 over a arctan of x over a plus c. However, here we have x as like the solo variable here, but here we have v over square root of 2 to the power of 2. So I want to just only have one letter here. So I need to find a substitution for v. So when I'm using the standard integral formula, it will be clearer, and it could be something that's more easily substituted in this formula. So let's let w equal to v over square root of 2. So dw over dv, we take the derivative, will just be 1 over square root of 2. So we can isolate dv, find a substitution for it. So dv equals to the square root of 2 times dw. So that means we can rewrite this into square root of 2 dw, right? Because we are replacing dv. We are replacing this entire thing, and let's have the rest. So that's just w squared plus 1 squared, if you want to be clear about it. You can pull out square root of 2 if you want to look neater in the integral. So you have w squared plus 1 squared dw, and that is like, this part is really straightforward if you want to apply this, right? So that means you will end up having, let's leave square root of 2 outside, and so 1 over a is just 1, right? So we have 1 over 1, which is just times 1, right? I'll write the full thing here. Arctan of x over a, but however x is w, so we have w over 1, which is w, and then plus c. So we can make it simple here, and we can just write square root of 2 of arctan. So this is w, which is v over square root of 2. So we just have the original thing here inside. Oh, sorry. Flip to a new page. Plus c. You don't have to write plus c when you are adding up everything together, but just remember to add it in the end when you are done with the entire thing. So yeah. to solve the other part, we are applying partial fraction decomposition. But before doing that, we should also find a substitution for v over square root of 2 to make things easier. So let z equals to u over square root of 2. So dz over dau, which follows the same thing as above, like here, we just have 1 over square root of 2. Right, so du this equals to square root of 2 times dz. So now we can rewrite this thing into something of a similar structure, but just with a different sign as the one we have above. So this is just, let's take square root of 2 outside, and that's just 1 over d squared minus 1 squared dz. Right, so, and remember in partial fraction decomposition, we want to like factor this, right? So this is just a squared minus b squared, that equals to a plus b times a minus b, right? So it's easy to write this into the product of some things. And that will make us ready for partial fraction decomposition. That's just z minus 1, z plus 1, dz. I will solve this partial fraction decomposition on the next page because we're running out of space. So what we are solving is this. I'm just copying it down what we wrote on the last page. This fraction equals to a over, let's have d minus 1 here. Sorry, let's have d plus 1. Yeah, d plus 1. Plus, well, the order doesn't really matter, but like I prefer to have d plus 1 first. And d minus 1 here. So if we multiply on both sides the numerator by z plus 1 times d minus 1, we will have 1 equals to a times z minus 1 plus b times z plus 1. That equals to 1. So we're solving for a and b because we want to write this into two separate complex rational expressions, right? So if you just try to insert some variables and make the two sides equal, you end up having a equals to negative 1 over 2, b equals to 1 over 2. It's just that you want to make sure the terms with z will be gone in the end, so this must be like opposite, right? Like one is the negative value for the other. And you want to make sure that a times negative 1 and b times 1 will give you 1 in the end. So these are the two values that we need. So let's rewrite the previous integral. Rewrite. So we had this. So now that equals to square root of 2 times the sum of two separate integrals. So we have negative 1 over 2 on top first. That's over d plus 1 dz. Then we have plus the other one starting with 1 over 2 on top, and then d minus 1 dz parentheses. So we can make this simpler. We can pull out this factor, right? So, well, we'll just end up having 1 over square root of 2, and well, we can write this first. So yeah, we can have 1 over the integral of 1 over d minus 1 dz minus the integral of 1 over z plus 1 dz. Right, so now it's becoming very clear. This probably reminds you of like ln, right? If we take the integral of that, that becomes ln, remember absolute value, ln of d minus 1 minus ln of d plus 1. So we're making this very basic right now. And we can combine this, right? Remember, like, if we have log A minus log B, we have log of A over B, right? So let's just combine what's inside the parentheses. So we end up having ln of just d minus 1 over d plus 1. And we can substitute u back right now, so because we need to substitute everything back later, right? So let's just do some work right now. So d is u over square root of 2 minus 1, and then just the thing now becomes plus 1. Oh, why did I copy it twice? Plus 1 right here. Well, we can multiply the numerator and denominator by square root of 2, right? Because this fraction looks kind of ugly, so we can stop here in when we have u alone with something. Plus c if you want to write it, but it's okay if you don't right now. So we're done with the two separate parts for these two right now. Our job is to remember to multiply them by 1 over 2 and substitute everything we had back to where they should be and simplify, combine if we need, and then we will end up with the final answer plus c. Well, I guess I missed something here, so this should be plus, yeah. And now our job is to substitute everything back and combine, and let's write the original thing. Integral of square root of tan x dx equals to, well, we ended up having, like last time, we had, so that's, yeah, v over square root of 2 to the 2 plus 1 dv, then plus something for u. So that should be minus du. We had this last time, and now we're putting back what we have here and what we have here. So that's just 1 over 2 times the substitutions. That should be square root of 2 arctan of v over square root of 2 plus 1 over square root of 2 of ln absolute value of this part. Right, it's gonna get even more messy, trust me. So now let's start putting back t. Like, let's apply this one. So now we have v is this t minus 1 over t. That whole thing over square root of 2. And plus well, we can start getting rid of this, right? Like, get rid of that extra parentheses. So that's just 1 over square root of 2. And for this one, we have 2 square root of 2 in the denominator. Then ln, for u, let's just put back u, t plus 1 over t minus square root of 2. I'll just copy that. Right. We can make the top and bottom a bit more neater. So, well, let's say if we, for arctan, let's multiply the numerator and denominator inside by t. So we have t squared minus 1, then t of square root of 2 plus one over 2 times square root of 2 and ln. Oh, for this one, yeah, we can also remove this like 1 over t by multiplying the numerator and denominator by t. Because we don't want to have like 1 over square root of 1 over square root of 10x in the end, right? So and now we can just start putting back the values for like t. So we're putting back square root of 10x. Another hard part in this problem is that you want to be super careful when you are substituting values back. It's just kind of easy to make errors here and there. So since t is square root of 10x, we can have square root of 2 10x here, right? And then plus so that will be 10x plus square root of 10x. Oh, sorry, that should be 1. 10x plus 1 minus square root of 2 10x. The bottom just, like, the denominator just differs by a sign. Yes, we are almost there. So if you prefer something slightly different in the parentheses of arctan, if you don't like the square root of 2 tan x as the denominator, so we can do a little modification. We can divide the numerator and denominator by square root of tan x. So here we have square root of tan x minus, we have 1 over square root of tan x, so that just minus square root of cotan x. And then the bottom, like the denominator, will just be square root of 2. Yeah, so that's the full answer. And if you solved using, plus c. If you solved using hyperbolic tangent, your answer should look like this. So I will write it on the bottom. It's similar. I'll just copy this thing. It's the same here. Minus here for the second part is just slightly different. Arctang of something similar. This. We have plus here, so looks kind of similar, but plus c. So that's the full solution. And thank you for watching.